Resume with the second talk of this morning session. It is my pleasure to introduce Reeve from Liverpool Hope, and he will tell us about singularities of equidistance and supercaustics in 3 space.
Okay, thank you very much, Matthias. Okay, so first of all, I'd like to thank the organisers, Eugenio, Vinicio, Federico, all the other people who have been involved, and give me the chance to come to Mexico City, visit this great university and this wonderful city, and give me the opportunity to talk in this so far wonderful conference. So I say this is my first time in Mexico. In fact, it's my first time in North America, so I've ticked another continent off the list. But so far, great times. Thank you very much. And so this is a joint work with Peter Giblin from the University of Liverpool. Okay, so I'm going to talk about caustics and supercaustics. So let me first say something a bit about caustics. In particular, here's some motivation. So caustics are everywhere. And here's some examples, be it in your coffee in the next coffee break. We see this curve here. This is a nephroid curve, well, half a nephroid curve, if you complete it around like this. And we see there's a cusp here in the light. So the caustic is where the light is focused, either for example, by the cup, or by the glass with the liquid with the beer in. Or here we see another caustic. Here is a cusp here. And then in some water we have all these caustics here. So where the light gets focused by some medium, and then we see it as a brighter area. This one on this mezcal is not too, maybe you can't see, but there's some like little caustics around here, but maybe not too clear on the projector. Okay, so this is the motivation. These are some caustics. And some more recent applications of caustics is in astronomy. You have this phenomenon called gravitational microlensing. And this is where if you have some distant object, if the light from an object has some intermediate object, for example a star, this intermediate object acts like a lens and can actually magnify a distant object. So, so here we see there's some intermediate object, maybe a black hole or something, and these are distant galaxies, but they've been magnified and smeared around the outside. So this is actually a same copy of this and this. These are all copies of the same galaxy that have been magnified by some intermediate object. And in fact, these microlensing gravitational caustics around these points, this is where the magnification is greater. So I mean, the reason this has been known for a while, but it's becoming more significant now because of improved engineering and so on. We can actually use this to study the properties, small changes. We can study the distribution of matter in the galaxies, the universe, and also detecting exoplanets. But that's just some motivation. So here I'm going to draw the same pictures that Statchek drew the other day. I think his were slightly better. They were a lot cleaner and crisper, so apologies for that. And he had nice moving curves, but this is just a simple curve. So we start with a plane curve. This is convex, doesn't have to be convex though. We consider pairs of points on the curve such that the tangent lines are parallel. So for example, this line is parallel to this, and then what we do is we draw a chord joining this point, an infinite straight line between the 2 points such that share parallel tangent lines. So there's another point, there's a few more, and there's some more, and some more again. And you can start to see this curve forming here. We have these 3 cusps. And see, this is called the caustic. It's the envelope of the lines, just like we saw in the envelope of the light rays in the glass. And we can also, this is called the caustic, but what the equidistance? The equidistance is we can consider, we can introduce a coordinate along these lines, which is called lambda, and introduce fixed distances along this chord. So by increasing lambda, we move along these, and these give us these curves. And these can have singularities, for example. Here's the blown up version of this. Here's the caustic, and inside we have the equidistant. Here we see it undergoing 3 swallowtail transitions. And that's the caustic. Okay. Oh yeah, so this is if we choose lambda to be equal to half, this is called the Wigner caustic, which Wojciech knows a lot, has worked upon. And it's okay, so let me just zoom. So we can work with 2 local pieces. This is a piece of curve, this is another piece of curve, and we'll call this y, use some function of x. So this epsilon is a parameter. So I'm going to talk about families of curves. So epsilon's moving. So, but this is just for a fixed epsilon. This is a curve y equals f of x. Fixed epsilon. This is a curve y equals g of x. So there's a chord we introduce between the two, and then we can introduce this coordinate lambda or barycentric coordinates, lambda and mu, such that lambda plus mu equal to 1. Here, so when we're at lambda equals 1, we're at this point. When we're at lambda equals 0, we're here. Lambda equals a quarter, say here. And lambda equals a half, this is the Wigner caustic when we're here. Okay, so the equidistance, what we're going to talk about, is the image of this map 1 minus lambda plus the one piece of the curve times lambda times the other piece of the curve. So you see when lambda equals 1, this part vanishes, we're at 0, and this is just equal to 1, so the coordinates are given by this curve. When lambda equals 0, then this part vanishes and we're at the other part. And it's just a straight line because, well, lambda is linear, so it's just a straight line joining the two. So subject to the parallel condition, the f is parallel to g. This describes the equidistant we need. Okay, so let me just, okay, so as I'm going to come on to supercaustics, but first let me talk a bit more about the caustic. Okay, so let's consider the space. So we're still working, so this is the plane that we're working in. So, yeah, this is a plane in which our curve lives, the r squared, and r is just the parameter lambda. So for each fixed value of lambda, we get one of these equidistants. And so we can consider what's called the affine extended wavefront, which is the collection of all of these slices of equidistant living in the space. Oops. So it's just the union of all the affine equidistants with its own slice in extended affine space. Okay, so now we have all these collection of wavefronts, equidistants, and then the caustic is then the singularity. So this is this surface. These are all the equidistants spreading out over lambda, and then the caustic, or sometimes called the center symmetry set. So the center symmetry set is the specific example of the caustic for this particular problem. So the center symmetry set is defined to be the singularities of the projection of this set in the extended affine wavefront. So we project this down to our original plane. So this is what so I call it Q1, Q2. That's just the plane where the curve lives. So we project it down, and we get singularities. So there's two types of singularities. The first one is the singularities of this affine extended wavefront itself. So this projects down to here. This is the caustic, and we also have the criminant, which Davidov also had in his talk. It's the at least in the picture there was where it's singularities of the projection of this back down to the original space. Okay, so we have caustic in red and criminant in purple. Okay, so this is well known. This is caustic in criminant, but now I'll come on to supercaustic. So, so the original way that was approached by Vladimir Zakhalyukin and Peter Giblin, 2007, was using this so-called generating family. So you have a map. So this is the plane case. So we have S and we have T. So S is the variable on one curve. T is a variable on the other curve. Lambda we have is the affine time, and Q is the plane, and N is the normal to the curve. And so the normal you can consider, because we're working locally, so we can consider N equals N1, N2. So this is the normal, but because we're local, we're in this direction, we can divide by N2. So it's just N equals N2 and then 1, and then we can recall this N1 tilde. So actually, we can think of N as being one-dimensional, or being one variable. So, subject to this condition, this describes exactly the equidistance for our curve. So this is so the gamma 1 is a piece of one curve, gamma 2 is a piece of the other curve. I was using F and G before, but I changed. And remember, mu was 1 minus lambda. So again, when lambda is 0, we're at this curve, and when mu is 0, we're at this curve. And so the condition F equal and this, I should say, these angled brackets, this is like the scalar product. So I mean, we're in affine space, so it's not really just the dot product, but you can think of it as a dot product. And so when this vanishes, this means Q equals to the ratio of our two curves, so this gives us the equidistant. And the point that df and ds by dt equals 0 means that there exists a normal that's parallel to both. So there exists an n that such that this is parallel to this. So this exactly describes our equidistant. Okay. So we have this function f, this map. This function f is this, and together with these conditions. So we can consider this map f tilde that takes sort of our variable space. So we have n is one-dimensional, s and t, lambda and q is two-dimensional. So we have from 6 variables mapped to the zero set of f equals fn, fs, ft, and we would need the inverse image of 0 is our extended affine wavespan up here. So this is this. Okay, so when this surface, so then we project down this to our lambda q space, which is this, and okay, so let me get this right. So we can have, so the caustic, so we have this surface in here, which in general will be smooth, but then we project this down pi 1, which gives us to this surface, which lives in here, you recall, and then we can have, so singularities of this projection gives us the caustic, and singularities of this projection gives us the criminant. But the thing that first started me interested in this was in the supercaustic was what happens if we go one level above. What happens if there's singularities up here? So if this is called the Lagrangian submanifold. So what happens if we have singularities in the Lagrangian submanifold? Then we have an extra kind of degree of degeneracy. So the supercaustic I define is of the pair, so the two curves, is a projection to lambda x space of the set of singular points of the inverse image of the zero set of this map. So essentially that's the points given by when this Jacobian, or when this matrix fails to have maximal rank. So you'd have your two curves, you introduce some local coordinates and write them in Monge-Taylor form, and then you can work out what the exact condition is in order for this matrix to have fail to have maximum rank. So yeah, so and that you can see happens. So you get a lot when you calculate this, you get a lot of ones and zeros and things cancel and then so on. But this fails to have maximum rank precisely when f2 is equal to 0 and when g2 is equal to 0. So this corresponds to the case. So I didn't really introduce what f and g was though. So we say f equals, so g equals g to, I used s and t, didn't I? S g to t squared. Now we can always assume it starts with quadratic terms because we're taking these two things to be parallel. And up to some affine change of coordinates, we can always take it to be starting with at least quadratic terms. And so the point when the supercaustic occurs is exactly when you get when this is equal to, when this is equal to 0 and when this is equal to 0. So if both our curves start with cubic terms, so in other words, if you both have two inflections, that gives rise to the supercaustic. But the point is, so when can we have? We're interested in generic geometry. So, point is, if I draw two inflections in the plane with parallel tangents, as soon as I perturb this a little bit, then this situation will disappear. So this is a non-generic situation. However, it does occur if we consider one-parameter families of curves. So if we shift the curves in such a way, if we just consider a family of moving curves, then this will be unavoidable. This will happen for a generic family of curves. So that's what I just said. And so in fact, the theorem for two generic submanifolds, in fact for any manifolds in any space, the supercaustic is always going to be empty. You have to consider at least one parameter families. And one parameter families is enough for hypersurface case. If you have lower dimensional submanifolds, then you need even bigger number of parameter families. And that's essentially, this is why I had this x and e here. So epsilon is a parameter that we introduce in order so this curve can move in such a way that they become parallel with inflection points. So this is the supercaustic. So in the normal case, for equidistance, this is shown by Peter Giblin, Zakaljukin, that you get the following. In fact, also earlier work of Statscheck as well. So these are the things that can occur. So in the plane curve case, we have smooth line, we can have cusps, and we can have swallowtail transitions. So this alpha, so the Q1 is the space. These don't depend on time because there's no lambda. Here, this does depend on lambda, so this has this change as lambda varies. But I've switched lambda for alpha because lambda's, as you know, varies from 0 to 1. But what we can do is we can consider, say if we're interested in this point, what's going on, we can say lambda equals lambda naught plus alpha, and then, well, this is some constant. So this could say half or something, and then alpha is then a small parameter. So for the normal form, we use alpha. Okay, so all about the supercaustic. So for this to occur, we need, say we need these two parallel inflections. And this can happen in two obvious ways. So we can have, if the inflections are kind of facing opposite directions, or if they're in the same direction. These will give our two distinct cases. So in this case, there's only there's no parallel tangent points apart from these 2 points. Whereas here, see this point is parallel to that, and also to that, and to this. And so this is, but in both cases, what happens to the supercaustic is that the whole chord becomes part of this is the caustic. Well, this is the supercaustic, and hence part of the caustic. So we have this extra line that joins these two where it's caustic. Okay, so say this happens in two families, so we can introduce f is some function in x and epsilon. G, we can say, oh yeah, I missed a +1 off here. So that after an affine transformation, we can move this. So this is at the origin, and this is at the point 0, 1. And this is how we can take a generic family in this way. So epsilon here, epsilon, and so on. And then so we consider, this is how it looks. You have two moving curves, and at some point, say here, now we have two parallel inflection points. So you see it moving, and then if I can stop it at the right point, so there, hang on, no, that didn't work. Anyway, okay, so at that point, there are two parallel inflections. This will happen in a one-parameter family of curves. It's unavoidable. And so these are the two situations. We can have them facing opposite directions or facing the same direction. And in this case, at the epsilon equals 0 point, we actually have 4 pairs of parallel curves. So for a given value of s, we have 2. So for a given s, we have 2 in t that are parallel. Whereas here, we just have an isolated point where they're parallel. So here, this line, there's no parallel tangent to this on this curve anyway, because this is going this way, whereas that's going that way. Okay. So these are our two curves. Again, this is the image of this map which we want to give our equidistance. And the new approach that I was considering is or me and Peter have been working on, is to consider, rather than the method that Zakaljukin and Giblin and I've used before, we're going to use, instead of using this like Lagrangian Legendrian map, we're going to use this 2-parameter family of maps from the plane to the plane. So here we have it. So we have the first coordinate is given by, because we write our curve as s, then f of s, and then t, g of t, for example. So then it's lambda plus that, plus 1 minus lambda times that. And so this is just expanded in coordinate, and then minus, well, we don't need the minus q because we're giving a map. So instead of having the condition that f equals 0 and solving for q, we have the image just of this into the space, into the plane. So it's a 2-parameter map, s and t, 2 variables, into this map with unfolding parameters lambda and epsilon. Or sometimes I'll use alpha instead of lambda. And okay, so we have this, and then what we want to do is we want to try and reduce this to a normal form. So what we can do is we make the substitution, we make a change of variable, so we're going to introduce u into here, so we solve this for u, and make the substitution t equals this. And that makes the first coordinate u, and we have some function h of a new variable u and s and unfolding parameters. So I've switched from, this should be an alpha here really. So alpha and epsilon. And these are unfolding parameters. So now it's just a case of seeing what singularities can occur. And so studying this function, so we can expand it in a Taylor series and look for these so C3 naught, C2 1 are coefficients, which can vanish depending on the initial conditions for the surfaces. So different, what can happen? So this, first of all, this term can vanish. So we can have, okay, so we have this occurs in one parameter families of curves. So at isolated points. So we have no more conditions on our original surfaces. However, we still have lambda. We can choose a value of lambda to give us, any point in this chord. And we can choose lambda or lambda naught such that these coefficients can vanish. So we're only allowed one more degree of freedom, really. So what can happen? Either this can vanish, C3 naught. This gives us the first case. In fact, no, that's the only case. So this will vanish exactly when lambda naught. I just realized I've switched to, okay, so F3 or F3 0, because if, this is, the 0 is because epsilon is 0. This is just the term in x cubed. So if the x cubed vanishes, so this is a coefficient of x cubed, and this is the coefficient of s cubed, sorry, and this is the coefficient of t cubed. And so when this happens, when lambda naught equals this, so some relation between the two curves, this gives us a special point on the chord. Okay, so sorry, I should have said, yeah, so case 1, this is where they both have the same sign. So that was this case. If they both in the same direction, we have a supercaustic chord, but we want to know what's happening to the wavefronts. And so at a special point, something else is going to happen. This can vanish. C3 naught equals 0. Whereas in this case, so there's an extra special point, whereas in this case, there are no special points. But let's look at what's happening on the actual chord elsewhere. Okay, so away from this special value, which I'll consider in a moment, we want to know what's happening to first of all, what's happening to the equidistance. So as we take different equidistants, what's going to happen along this curve, how are they going to look, what singularities are going to happen. And so we consider both these cases separately. And it turns out in case 1, what happens is on this chord, you have a beak singularity. And on this case, you have a lip singularity. So essentially you just reduce it to this normal form. In the case when F3 and G3 are positive, F3 times G3 is positive, you get this normal form, whereas F3 times G3 is negative. So the sign is opposite, means you have this case. We can reduce it to away from the special values, so away from when lambda is 0 and when lambda is 1, and this special value in this case, and just here and here in this case, we get these two normal forms, beaks and lips. So for fixed values of the wavefronts, as we move epsilon, so we start off with, so just a fixed value of lambda, we have this lip shape, and then as you move epsilon, it degenerates at this point, it becomes a single point, and then we have the empty set afterwards. If we have them the same directions, pick a generic value of lambda away from the special value, you get a beak singularity. So these equidistants undergo this Beek's transition. So Becker-Beck, as René Thom called it. And so it's like this. So pick a non-special value of lambda, we have these two beaks come together, and then they move off as two separate curves. So in the special value of lambda, what happens is, so when lambda naught is equal to these special conditions based on the curve, we can reduce by A equivalence. A equivalence is what I'm using all the way here, because this preserves the equidistance. You can reduce it to this normal form, so S5 plus S4 plus squared U, where these are the unfolding parameters. Subject to these conditions which won't occur generically, so this will be more degenerate case that we don't consider because it's avoided generically. Okay, so this was given as in Riege's list as called 11.5, this singularity, and also been called the goal singularity by Terence Gaffney. And this is what it looks like in the epsilon alpha plane. So at each point in the epsilon alpha plane, so you pick a value of an epsilon lambda, and you want to know what the equidistance look like. So this is what it looks like here. And on this curve, we have this Beek's transition. So these two come together, They meet on this curve and then they move off separately like this. And then you also have a so this is the goal point. You also have a swallowtail curve coming in here which has second order tangency at this point. And we also have a self-intersection, self-tangency point here, and two, so the two intersect down here below the curve. We have 2 points separate. They come together on here, become tangent, and then they move off and go off here. We also, in the paper I did with Peter, we also looked at the, what did we do? But I won't talk about that now, so anyway. Okay, don't worry about that. Right, so, yeah, so this is another place. If you're wondering where you've seen the singularity before, it comes up similar to Alexi's picture. We have the sombrero here, and this is the parabolic line. And this curve here, this is where the asymptotic direction has higher tangency with the surface. So at certain points we have our goal singularity here, which is this one, and also some others. So we have, this is 6, this is a swallowtail point, and also at 5 we have so-called goose singularity. So this is another way where goals, and as far as I know, I don't know of anywhere where goals have applications, but they do here and also in these equidistant special points. So there's also this goose, so we have all the other points, but the question is all about the goose singularity. So this has x cubed, y. And then, so this has this transmission. The question is, does this happen in our case? And the answer is no. We get no Geese singularity because this occurs at the transition between, at the closure of the beak stratum and the lip stratum, other way around, the beak stratum and the lip stratum. But as I said, in this case we have beaks, and in this case we have lips, so the two can't be the same. If we had higher order, maybe if we had a quartic, consider a bigger parameter family of curves, if we started with quartic terms maybe, but that's non-generic. So we don't get goose, even though this is the same codimension as the goals in this case, but it's avoided for geometric reasons. Okay, so here we have the equidistance for one parameter family of plane curves, so smooth, curved, cusps, lips, beaks, and the goal lies between the swallowtail and the beaks transition, and we also have butterflies. The reason, you can see from the goals picture, so we have swallowtails nearby and we have beaks nearby, so it's the closure of these two stratum where the swallowtail has second order tangency with this other curve. So, question is, what about happens if we move into the third dimensions? 2 dimensions, all well and good, but we live in 3 dimensions, so and of course when we go into 3 dimensions the geometry becomes richer and yeah, so it's harder, but more interesting. Okay, so we do the same setup. We have, instead of 2 curves, we have 2 surfaces in free space. Instead of tangent lines, we consider tangent planes, and then we draw the infinite chord between them. So here's a lot of chords, and then we can take either the envelope of these chords to give the caustic, or we can take a fixed distance along, say lambda equals the third, to give us the equidistant. Okay, so equidistance for 2 surfaces in free space was done by Giblin and Zakaluk, and also Peter Giblin's student Paul Warder did some stuff on this. And so this is the case: A1, A2, A3, A3 star. This is swallowtail, beaks and lips, A4 and D4. And of course, so this is a subset of the Legendre singularities defined by, or given, classified by Zakaluk and also Arnold. So of course we don't have any A2 star. Oh, we'll come on to that in a moment. So these are the cases. We have a smooth surface A1, we have cuspidal edge A2, and also swallowtail surface A3. Okay, I should also say that I'm also particularly honoured to have the conference here in Mexico City. This is the perfect place for a singularity conference because of the large number of swallowtails that are here around the campus. In fact, so I've seen some huge, big yellow ones. This is an example. Papiloclesphalates, something like this. Anyway, we have a lot of swallowtails here. So take a look, some huge swallowtails. Good to see. And we also have swallowtail lips. So this is A3 star plus. So here we have, this is the cuspidal edge. So this is a birth of these swallowtails, and they go off facing opposite directions. Whereas swallowtail beaks are two cusps come together and then form this kind of like this bench of surface with these the cuspidal edge here and a self-intersection underneath. There's also the butterfly transition, D4 minus. Of course, I couldn't come to Mexico without mentioning the pyramid singularity. And also we have D4 plus, which is Perse. Okay, so what about the supercaustic case? When does this occur? And we go back, you look at the Jacobian, you find when it fails to have maximal rank, and the conditions necessary for the supercaustic in the three-dimensional case is that you have two parabolic curves, and that's the first condition, and also that the asymptotic directions are parallel. So if we have two surfaces, looking at the equidistance, we get parabolic curves. So this is one point of the surface that's parallel to here. So the tangent plane is a parabolic point here. Asymptotic directions are the same. Then that will give us the supercaustic. And this happens in a one parameter family of curves. So if we stop it at epsilon equals 0, so there, cheat a little bit. But anyway, so here we see this is now a parabolic point at the origin, and also the asymptotic direction going up here on the same on both surfaces. So this will give us the supercaustic. And again, this occurs in one parameter families of curves at isolated points of the family. And so again, we write these locally in the surface in terms of x and y. Epsilon's the parameter family, and also x and y, epsilon here as well. So, okay. Again, then the generating family is now given by, again, the same, the image of these, a ratio in lambda of these 2 points on the surface, subject to the tangency condition. Again, we work away from the two submanifolds themselves. Okay, so now before we use the maps from R2 to R2, in this case, we're going to use maps from, we have two surfaces, so we have two variables on this surface, two variables on this surface. So that's 4 variables, but we're living in free space, so we need to consider maps from R4 to R3, subject to this, so it's the image of these points, so it's S1, S2, and T1, T2, and then some surface in this point. So again, we can make a change of coordinates. So we're only considering co-rank 1 singularities because we can make a change of coordinates. So the first coordinate becomes U1, second coordinate U2, and then some function in H in all the other variables. So it's a case of classifying maps from R4 to R3 and then considering the 2 parameter unfoldings of this. Okay, so it's just subject to the conditions. So if we look at, we want to know what these wave fronts are, it's just the image of the critical set of this map. So it's just you take so you work out what the conditions for the Jacobian to have less than maximal rank. So it's just, it works out that it's just this H by S1 and H by S2 are the conditions. Okay, so this is our map, and we write the surface in Monge-Taylor form with some coefficients F20, G20, and so on. And then, so the first case is when, so first of all we consider where nothing vanishes, but then, so in particular where this curve doesn't, this curve, this one can vanish, S1 squared, and the other one that is interesting that can vanish is this term. So if this S2 cubed term vanishes. So the first case, so first of all we'll consider this as non-zero because that's a bit more complicated, we'll come on to that in a moment. But the other case is when CO3, 0, 0 vanishes. We call this, I've called this Q as well. So when this vanishes, which will happen for some specific values of lambda, we're going to get these, again, like these special points, just like we had the goals before here. We get special points in some cases where that can vanish, and that's going to give us this normal form. That'll give us some normal form, but away from them special points, so just the normal, nothing vanishes, nothing special happens, so we have just some term S1 squared, S12 cubed. We can reduce it to this normal form up to A equivalence for some variables A and B, and then we want to reduce it further, so we consider what happens. So consider the, supposing that quadratic form So subject to conditions on, I've reused different terms. This bracket here. So depending on this quadratic form, S2 and then in U1 squared U2, if this is non-degenerate, well, this will happen, well, as soon as this is not, we have no more conditions on the surfaces, this doesn't contain lambda, so this will be non-degenerate generically, so we can avoid that. But two different cases can happen. This can be, so this is just the condition that this is non-zero in terms of our original surface and curve. So if this is non-degenerate, there's two different cases that it can be reduced to. Sorry, three different cases it can be reduced to, where we have plus minus and plus minus, so where these are independent, so we can have plus plus, plus minus, minus plus, or minus minus. And so this, away from the special values, is what is the normal form for our equidistance. And so this singularity is free A determined, and it's versely unfolded by the parameters epsilon and alpha. And so these are the different cases we can have. Plus plus, so-called flying saucers. So we have or Zeldovich's pancake, sometimes called, and where this flying saucer vanishes to a point and then disappears. Yeah, and then there's also this. This is called by Viktor Gorinov, gives us the catchy title of this is a hyperbolic transformation of an edge, and this is called the def of a compact component of an edge. So rather catchy. And this is the more catchy title of Zeldovich's pancake or flying saucers. So I remember a story from I mean, this is the wavefront, so not considering the caustic, but Zakhalukin originally suggested that perhaps that these singularities occurring in the caustic is what gives light to the UFO sightings. Because if you have some dust or gas, and then if the caustic falls in the right way, you can see these kind of things emerging. So that was his idea for why we see flying saucers, but then later it was proved by Chekhanov that this doesn't happen for optical caustics. But that's, in that case, you need the Lagrangian to be smooth. But if we have Lagrangian to be non-smooth, then this can happen. But unfortunately, it also doesn't happen for optical caustics. So still still not an explanation for UFOs. So they could still be out there. But okay, so these are the three types. So, but then as we had before, we only had two types, but there was only two scenarios. So, but the question is, how can you have these two parabolic surfaces with parabolic asymptotic lines? What are the possible cases? The possible what kind of possible settings can you have? What setups can you have where there's considering the sets of parabolic sets of points on this surface, such that there's a tangent plane parallel on the other surface. So this is the interesting question. And we have these different cases where, depending on the sign of F3, G3, QR, R was this condition here, that this is non-degenerate, Q was this condition. So it's all related to the initial geometry of the surface. And you can also consider the Gauss map for these two surfaces, because the Gauss map is just you take the normals to the surface, and obviously the normals of one surface to the other surface is going to be, they're going to have the same normal. So if you have to take the Gauss map for both surfaces, you want to see what the region that's contained in both surfaces. So when you take the Gauss map of a near a parabolic curve, you have this fold, and then so you have some surface like this. You take all the normals, it gives you some surface like this. So it gives you like some fold surface or a double surface like this. So because all the normals, because the normal here is the same as the normal here, so it maps two to the same. So for one surface, so this is the parabolic fold, the fold of the Gauss map on one surface. This is on the other, and then if this region occurs on one and this region occurs on the other, the region that occurs on both is inside. So these are all the possible setups you can have for the two Gauss map regions that are covered by both curves. So I've called this AC, B and D. AC, because this is kind of like two scenarios you'll see in a moment. There was AC, B and D, but A and C are the same, essentially. So we can have just a region here that comes like this, and then it still stays as one region. Here we have one region, it becomes two regions, and here we have no regions, and then we have a single point, and then we have a compact region. So again, this is another way you might like to visualize it. So this is the one of the Gauss, it's kind of like a a schematic version of the Gauss map and the projection down to here gives the regions. So these are the possible scenarios. And so, I mean, here we can see so the two Gauss maps can kind of come together. So you have your parabolic curve like this, another parabolic curve like this. Here we have a kind of a non-compact region like this, and on this surface we also have a non-compact region on here. Or you can have one surface like this, and then there's no points, and then you move it, and then suddenly you get a region of points. And this is case D. So if you just move this, if you switch these two surfaces over, you see it's the same. You can have the complete region on the bottom and the disjoint region underneath, or it can be the other way around. Whereas these flipping doesn't make any difference. This is why this is two cases. Okay, so this is just saying, okay, so this is what happens. So what happens to the wavefronts in these cases? In this case, case B, we have this singularity all the way down with no special values. The hyperbolic transformation of an edge. If we have this case, AC, so I'll go for this one. If we have case D, we have none, then we have just one parallel point, and then we have two regions. This gives rise to flying saucer case only, and again, no for, actually there is another degeneration, but no degeneration. The point is you can't have, if you have this case, then the coefficient of S2 cubed can't vanish. So that's what I'm considering first. So S2 cubed can't vanish in this case or this case, but in this case we have special values of lambda such that the S2 cubed term vanishes. So in case AC, this could equal 0, and so at special values, this is similar to the old formula. This is why, and then you can be reduced A equivalently to this map. And again, then it's firstly unfolded by, say, epsilon and lambda. And so we have this map. So this is one of this, I mean, this occurs, you may recognize this. This is a slightly different form, but this is so in the classification of maps from R3 to R3, this occurs. So this, if you ignore this S1 squared, because if we take the derivative with respect to S1 as 0, that just means but S1 is 0, so this disappears. So the plus and minus don't really make any difference. This just vanishes. So we only have one type. But this singularity in, say, the thesis of Raoul, and also in paper by Varitari and Ton Marat, also perhaps Victor Gorinov, they call it something like singularity 4, 2, 2. But for me, this is just the 3D version of the goal singularity in the last one. And it looks like this. So here again we have the alpha epsilon plane. So each of these represents a different value of alpha and epsilon. So here we have, this is a swallowtail point, another swallowtail point. Along here, these two swallowtails kind of bend around like this, and then make a beak singularity here. So this closes off and makes this kind of ring of fire down here like a circle here, and also this line. So this, and as we move across here in this direction, these two branches come into coincidence, and we have the Beaks transition. So along here, we have this Beaks transition. So if we move through epsilon, undergoes Beaks, whereas up here it undergoes this. So we have this as the ellipse as we go across here. This joins, one of this branch here joins to that, and it undergoes and then becomes like this. So the two cuspal edges come like this, and then they go off like that. So this is the hyperbolic transformation of an edge. So this is A2 plus minus. So, sorry, I said that wrong. This point, sorry, is this smooth surface comes into contact with this smooth surface. They come like this, like two bowls come together and touch, and then give birth to this circle. Then it goes round and they intersect, and we have the beaks, swallowtail beaks here, and over here, this thing. If we watch this part as it goes down, this goes down, and it vanishes at this point, and then becomes a smooth surface. So we have A3 plus minus. So the goals is the closure of the stratum of A2 plus minus, where it changes to A2 minus minus, and also A3 plus minus becoming A3 plus, so A3 star minus and A3 star plus. So this is what the goal singularity looks like in 3D. Okay, so that's all well and good. How much time I have? So this was the first one, this cubic term vanishes. But there's another thing that can happen. This is what we call case 2. What about when the S1 squared term vanishes? Now this This is a little bit more complicated, and I suppose I should apologise at this point, because I thought when I applied for this conference and submitted my abstract, I hoped that this would be done by now, but it's turned out to be a lot more complicated than I first thought, because when this term vanishes, the normal form is now the best that we're able to do so far is to reduce it to this normal form, which, as you can see, has these moduli terms B, C, D, and E. So we somehow seem to have these 4 moduli terms, first of all, I thought I didn't believe it, but I'm coming to believe it now. I mean, and then maybe we can get rid of one more. Maybe C can go, but it seems, I don't know how. But the point is, so for 2 surfaces, look at this is the 2 surfaces in free space. If we consider 1 parameter families, we have A4 star. So we have cusp, swallowtail, beaks and lips, butterfly, D4 plus minus, so persons and pyramids, A5, so-called wigwam singularity, or sometimes called elder butterfly. Then you have butterfly plus minus, also D5. And so the gold singularity we're seeing lies between A2 star and the A3 star. But this new singularity, D4, I call it D4 star for when this happens. But the question is, where does it lie? I mean, it seems to be adjacent to A3 star and also adjacent to A2 star and also adjacent to D4. But we have these 4 moduli, so where exactly does it lie? So just expanding it, goals lies between plus and minus, A3 plus, 3 star plus, 3 minus, and we have 2 types of D4. D5 is the intersection of these 2. But where does D4 star fit into this? And so it seems to be some interaction between either D4 star plus, so you pick and choose, you have one from here, and one from here, and it's going to be some kind of a mixture of those, it seems. But how they all configure depending on the A, B, C, D, and E. I have a few more minutes, right? Okay, I'll just finish. I'll show you some pictures and then we'll be done. So the question is, how can we classify depending on B, C, D, and E? And this is the kind of open problem at the moment, is exactly how many different cases are there? How can we classify? I mean, the way we've been looking at it is just consider this map, taking invariants of like the number of cuspid ledges, try and look at the number of intersections. But the problem is the formulas are huge, so it's hard to classify. But if we take different values of B, C, D, and E, we get very different pictures. So here we see there's 2 smooth surfaces that are self-intersecting. This is just at the point epsilon alpha equals 0. You can unfold this in alpha and epsilon. So this is type 1, 2 smooth surfaces with 2 intersections and some degenerate contact here. Type 2, just some different values. We have 2 cuspid ledges that can be tangent in some way. Type 3, I quite like this one. This is two moths, or 2 pyramids, if you like, coming, not pyramids, 2 purses coming in together at epsilon equals 0. Or this is a moth surface, and this is a moth surface. This kind of looks like 2 moths that are mating. You ever seen them? They can stick their tails together. But anyway, so this is type 3. We change the values again. We have this surface of a strange one. So we have cuspid ledge here. So it looks a bit like 2 swallowtails, but there's no self-intersection. Here's an unfolding of one particular example. So I consider all the pictures. This is a closure of D4 purse with A2 star plus minus, and also swallowtail lips. So you see, you have these different choices of all these 3 and how they can interact. So maybe it could be the other way around. Maybe the swallowtail lips could be outside. But in this example, this is this picture for these values. And then at this point is this surface, and this is how it bifurcates. So we go across here. One of the surfaces becomes, we have a purse singularity. Then we give birth to a lips. And then this is just 2 smooth cuspid ledges. And then more on the other surface, you get the lips and then the purse, and so on. There's type 5, just an intersection. There's type 6. This is here we have, I quite like this one, so I'll show you this one. This is the flying saucer across here. But if we cross down here, we get swallowtail lips are born on the surface. This is a cuspid ledge all the way around, so it crosses over at one point here, switches over to the other side. Then the other one moves over to the other side, so now they're both on the same side. And then go down here, then they disappear again, the lips. And here is the empty set over here. So this is then we have this, which is 2 swallowtails upside down. Then we have this one, 2 self-intersections. This one is a 2 smooth surface. This one has 2 swallowtails and a self-intersection. This one has a swallowtail here and a self-intersection and a swallowtail here. There's this one which has, I don't know, 2 swallowtails and cuspid ledge coming in and then going off. type 13. This is 4 swallowtails all coming together. So you see there's a lot of pictures. So initially I thought this can't be right, but now I'm starting to think maybe there are all these moduli. And the point is this is unavoidable. If you have 2 surfaces and looking at the equidistance for 2 parabolic points, at some point on lambda this is going to happen. Depending on the initial, it can happen in any of the 4 cases, A, B, C, A, C or B, D. This will happen at some point and it'll be one of these points, but it's unavoidable. So here's just some questions. How can we determine all the invariants? What sense are these equivalent? I mean, if we take like if the pictures look the same, if it's equivalent to some values B, C, D, and E, we can say they're diffeomorphic. But are these individual types, so for example 4 swallowtails, are all of them topologically equivalent to each other of that particular type? Can we do a complete classification of maps from R4 to R3, and then this will be one of them, and there'll be other maps, of course, as singularities, which will be interesting. And also, this would be interesting as well for me, because I mean, talking about the super caustic and so on, and this equidistance is just an example of that. But if we could somehow look at and maybe this is too hard, I don't know, but like if there was a complete classification of Lagrangian singularities where the Lagrangian submanifold is singular, that would include all these classes, that would be really nice as well. And so that's it. So here are some references. I mentioned Raoul, Victor, Ton Marat, Varitari. Also mentioned Giblin. I didn't mention Holton. This is one of the earlier papers on the center symmetry set. Some references. Okay, so muchas gracias por vuestra atención y feliz cumpleaños Federico. And I just thought I'd close this picture. So this is it's called Cuquillo circular pyramid, and so this is a D4 minus singularity, if you like. And this is right next to the hotel, and it's free to get in. So I recommend you go and have a look. It's really nice. There's hardly anyone there, but it's really peaceful. There's also lots of swallowtails, and of course the D4 minus. So it's well worth a visit. And yeah, thank you very much.
Yeah, thank you for this nice talk with
thank you
all
much.
these pictures. You really put some effort in it.
Oh, thank you very much.
We have maybe some quick remarks or questions from the audience.
Yes, sorry. Okay. Yeah.
Very quickly.
Yep.
You showed that the symmetry set is
Yep.
a kind of singularity of supercaustic.
Yeah.
After this projection and so on. The caustic on the plane, the chords form the one parameter family of lines, oriented lines.
Yep.
And they always form caustic.
Yeah.
In the space of all lines.
Okay, yep.
All oriented lines form a symplectic space.
Yep.
In T space, this is T star S2 space. And the question is, for the space in R3, not all the families, 2-parameter families, form the Lagrangian submanifold.
Okay.
On the plane, always this Lagrangian submanifold.
Right.
But in 3 space, no.
Okay.
The question is, how does look like your investigations if this family is really Lagrangian, this family of chords?
I don't know. That's a good question.
Yeah, that's really not so easy.
That would be, yeah.
But
We could.
I would like to add this question to your question.
Sir, thank you very much. That's a really good question. I'll add that. It could be a question for you. That'd be really good. Thank you very much. But yeah, interesting. Thank you. Any more questions?
I think we should also give some time to the poster session in the coffee break that's
Yes, sorry about that.
coming now. So let's thank the speaker again.
Thank you very much.